Okay, so let's take a look at finding out how to apply the universal gravitational equation. You'll find some places where I do this equation, I change this D right here to an R because it really stands for the separation more so than the distance between the objects. The key, however, is it's the measurement of the distance between the center of mass of both objects involved. So I use separation because it fits in all the different versions I've taught of physics. Plus, the R keeps me from getting confused. But that's the only change I do to the equation. Okay, so applying it in this question here, we first need to go through and find the things we know and what we're actually trying to figure out. So the key is it's asking about the gravitational attraction the moon has for a person. So in this particular circumstance, that means in the beginning, we're not really caring about Earth at the moment. So the first thing we need to do is find gravitational force between the moon and the person. And since the gravitational force is dependent upon two masses, we'll use the mass of the person and we'll use the mass of the moon. From there, we need to see how far apart they are, which is given to us here, and then we can go find gravitational force. All right, at that point, we simply plug them in. We got our constant, we have our separation, our masses, we'll go for force. Plug all that into your calculator, and it should spit out an answer that looks a lot like. So that would be the force the moon is applying to the person. Now, the second portion of this question is it asks to compare this to the gravitational force that Earth applies to the person. Well, if you're on Earth, or generally I have the cutoff of if you're in the atmosphere and you're worried about gravitational force the Earth applies, then for the Earth, FG Earth is mg, with g being the 9.8. So in that case, it'd be 70 times 9.8, or 686 newtons. And as you can see by looking at these two numbers, there's a reason we don't really care about the force of the moon is applying to us in relation to how hard the Earth is pulling on us. So that's how we plug those in. Same thing goes on in number 2, but with one new weird wrinkle. This time we don't know a mass, we know the weight on Earth. And just like we found weight on Earth, gravitational force on Earth via mg, that means this 800 newtons for the astronaut we're worried about is the mg. So that means for this astronaut, the mass of the astronaut will equal that 800 times divided by 9.8, which is 81.6 kilograms. Then we can use the mass of the Venus. Mass of Venus, 6.05 times 10 to the... that's the radius. Really hope I watch my numbers well enough. But you get what I'm going for. So sorry, it should be the 4.88 times 10 to the 24th that I got from right over here, kilograms. And separation, we're assuming that the astronaut is on the surface of Venus. Otherwise, we need a little more information. So it's the 6.05 times 10 to the 6 meters. Plug them all in. 7 times 10 to the negative 11th times 81.6 times 4.8 times 10 to the 24th over 6.05 times 10 to the 6th squared. Don't forget the square. Plug all that into your calculator and it should come out to 726 newtons. Notice how this time it's very close to the weight that the astronaut has on Earth, and that's because the radius of Venus is fairly close to the radius of the Earth. and the mass of Venus is fairly close to the mass of the Earth. All right, same process goes on in number 3 with one other small wrinkle. This time we have the mass of the satellite, so we have mass satellite, and we have the mass of the Earth. And I've had this page long enough that I don't know why this is 5.98 and that one's 5.97. It is. Whatever. We'll just use it the way it is, so don't worry about it. All right, then we need to look at the separation between them. So we know the radius of the Earth, and so at the very least, we're 6.37 times 10 to the 6th meters above the Earth. But the satellite is 1,000 kilometers above the Earth, the surface of the Earth. So the surface of the Earth is this far from the center of the Earth. So we need to add these two. But we can't add just a simple 1,000 to it because it's 1,000 kilometers. So times 10 to the third, which means this is basically a million, and this is 6.37 million. So 7.37 million. Plug them all back into that ugly equation, 6.67 times 10 to the negative 11th times 1,000 times 5.98 times 10 to the 24th. All that over 7.37 times 10 to the 6th squared. And we should come out to 7.343 newtons, or however you really want to round that off in the end. So that's your general process. Make sure that your masses are in kilograms, make sure that your distances are in meters, and then plug them in the right spots. Watch out on question number 5, since it's asking you to find the distance. You're going to be solving for the r squared value or the d squared, depending on if you're looking at it written as here. From the simple algebraic standpoint, we'd multiply both sides by the d squared, which would cancel over here and make the left-hand side f times d squared, in which case we would then divide by f to get it across, and we'd be left with d squared equals g m1 m2 over f. Find that, take the square root, and you're done. Other things, there's several different conceptual versions of the questions on the back, and right here in number 6 where it says number 2, I see that periodically, and I still keep needing to go fix that in my original file. Should say number 5. All right, that's our examples. If you need more, let me know.